Okay, so today is the session number 3 on the semester 1 on Frobenius subalgebra lattices in tensor category. So last week we covered all these slides, which are supposed to play the role of introduction. So today we will start to explain the details by hand. So I will not recover the slides. I just wanted to come back a few minutes to this last slide regarding the Riemann hypothesis for tensor category. So I explained that there is a way to reformulate the Riemann hypothesis in this way due to Robin. So it's given by a bound for the sum divisor function. So for n large enough, you should have that. And I said that for in the tensor categorical framework, if you consider a connected Frobenius algebra in a positive tensor category, you can generalize the notion of divisor sum function this way, because then here you just consider the dimension of the Frobenius subalgebra, not the full lattice, but just the dimension. So it's always finite because in fact, you may not need connected here because you don't need this to be finite. You don't need to be the Frobenius subalgebra poset to be finite. You just need their dimension to be finite. And you don't need this to be a lattice. So in fact, maybe you don't even need to put connected here. And I said to recover and to generalize Riemann hypothesis here, we need two ingredients. We need to generalize that as written here, and to generalize that as written here. But in fact, this point, so I said we should specify the depth. Otherwise, it may not be true. This point, in fact, is just saying, because in fact, the image of exponential is this way, is 0, infinity. So this interval. So here we are looking for some number. So what are we saying here? We are just saying that this limit sup is a positive number. Is finite and non-zero. So in fact, this first part, which look a little bit mysterious due to this constant, in fact, this can be reformulated in a complete straightforward way. We are just saying that this limit sup is finite and non-zero. As long as it is finite and non-zero, then there exists a constant of this form. It just takes the logarithm or something. Yes, you get the constant. So, and in fact, the fact that this is finite and non-zero already say something regarding the theory of Frobenius algebra, or more specifically, the theory of subfactor. You can deduce, even from that, this is finite non-zero, you can deduce some information, assuming it is true, you can deduce some information regarding the intermediate subfactor, for example. You have here, for example, when you consider intermediate subfactor or Frobenius subalgebra, one point is to estimate the number, the size of the lattice. This is what the paper the Watatani, the paper due to Liu, Bakshi, the paper with the angle we generalize in this, I explain. They also provide a bound for the cardinal of the lattice. And in fact, this kind of bound can be useful to estimate something like that. You have to be careful here because you only consider the dimension. So it's not exactly what you need. It's not exactly the size of the lattice, but the number of different intermediate of same index, or here, the number of different Frobenius algebra of same dimension. But in any case, this is the same, more or less the same flavor. So by saying that, in fact, this is more or less of this size up to this constant. So yeah, the fact if it converges to if it is zero or if it is infinite, it is saying that one or the other is dominating the other. But here we are saying that none of them are dominating, so it's more or less. So this is already strong information. So this part may be reachable, maybe theoretically, maybe you can. There is something to do. It is a priori maybe reachable, but this part, of course, is unreachable because it will imply the Riemann hypothesis itself. But at least this one, because it reformulated this way, may be reachable. Anyway, so let me. So that's so this slide cover the. So remember that we are covering the paper of the same name, Frobenius subalgebra lattice in tensor category. So all this slide covers the introduction of the paper. So now let's start with the details. So let's start with the section 2 of the paper called Frobenius algebra. So now we will define everything in details slowly by hand. Okay. 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 So let us review some definition and fundamental result about Frobenius algebra. Let us review some definition. And that all. So as I said last week, for the basic definition of monoidal and tensor category, we refer to the book Tensor Category by Ettinghoff, Galecki, Nishi, Shostak. So for the basic definition of monoidal and tensor category, we refer to so what in the paper is called 15, but let me just write, as I said last semester, just the details. So Ettinghoff. So let me write it one time here, and then I will just say EGNO for the when I will refer to Ettinghoff, Galecki, Nikšić, The book is called Tensor Category. 2015. Okay. So this is a main reference, modern reference for this kind of aspect. So we will do some graphical calculus. And for that, we need to mention that it's okay using MacLane strictness theorem. So according to MacLane strictness theorem, which is mentioned and proved in the previous book, or in MacLane book, if you want to go further, we can assume that monoidal categories are strict without any loss of generality. And strict, which means so that monoidal categories are strict without any loss of generality. Strict means that you don't need to care about the associativity isomorphism. When you define, remember, last week I mentioned the associativity axiom for monoidal category. You have a natural isomorphism called the associativity isomorphism, if you like, and you have to care about that in general. But according to MacLane strictness theorem, strict means that it is MacLane strictness theorem that says that any monoidal category is equivalent to a strict monoidal category, which means that the isomorphism, associative isomorphism, is the identity. It's trivial. And so you don't need to care about this associative isomorphism when you draw pictures in a graphical calculus. You have to be, of course, you have to be careful. So we will use, when I say you don't need to care about that, in the usual features, for usual thing, if you explicitly look for the F symbol, for example, you can make some picture, but then it will involve some hidden associativity isomorphism will appear. So we will use graphical calculus. Interpreting diagram from top to bottom. So this is very important for good understanding how you interpret the diagram, because in the literature you can find people interpreting the diagram from bottom to top. So and also from left to right or from right to left. So we fix from top to bottom. So there are some advantage and disadvantage for that, but anyway. Okay. So you don't need much to care about if you are not familiar with the notion of strictness or etc. If you are interested, you can go to this book or go to my previous class several years ago. But we will not care about that in this class. So if you don't know about that and you are not interested in that, you can just omit this sentence. This sentence is just here to certify that graphical calculus is really serious, makes sense because of that. So you can forget all that and only consider graphical calculus from now. We know it is rigorous. Okay, so definition. Definition 2.1. So of course, during this section about definition, I will basically slowly recall what I quickly said in the slide last week. So a unital algebra object, but here we don't write object, but you can write object because it's not an algebra in the usual sense, it's an algebra object in a monoidal category. But usually we just say unital algebra in a monoidal category. Monoidal. It consists of a triple XME, where X is an object in C, is an object in the category C. M is a multiplication morphism. Multiplication morphism in this from space, from X tensor X to X, and E is a unit morphism in this from space from 1 to X. And so we depict this morphism as follows. So let me just write here. Define unital algebra. Okay, so the picture is the following. So the morphism M for the multiplication is just, so from X tensor X to X, and you write this picture. Okay. Let me maybe change the color. Let me write from X tensor X to X. Maybe I will write the diagram in this color. Just to change. Okay. So from X tensor X to X. So let me repeat that it's from top to bottom. For top, you start here, so X tensor X to X. Okay. And so you draw this picture. So this is in this setting, this morphism is depicted this way. And it is not just an illustration, it really makes sense rigorously mathematically. And the unit morphism is this way, from 1 to X. So we draw it this way. 1. Oh, sorry. Change. 1 X. So 1, here is 1, here is X. And in fact, usually in graphical calculus, the 1 is drawing with some dots like that. For example, when you consider a morphism, we consider, for example, evaluation or co-evaluation morphism from 1 to X tensor X. And in fact, you draw this way. You don't put anything. When you omit to draw a string, it means it corresponds to 1. And here, this means from 1 to X, X tensor X. And here, from 1 to X, you draw it this way. Anyway, you put so this means the identity of X. this mean E, and here you put some dot, it means 1. So it's from 1 to X, and this is E. Okay? And here this is M, if you like. So this is the way we will draw it. Okay. And so this satisfies, so you draw this way, and it will satisfy axiom, associativity, and unital axiom. This satisfies the following axiom. So associativity and unitality. So first we will write by formula associativity, and then we will write picture. So the composition M composed M tensor identity is equal to M composed identity of X tensor M. And the unitality axiom is M composed E tensor identity of X equal identity of X equal M composed identity of X tensor E. So it's an exercise to be more familiar with pictorial graphical calculus, to reformulate this formula into picture. I will write it directly. So this relation are typically represented as follows. Typically represented as follows. So the associativity will be something like that. So M from top to bottom. Okay. So you start by there. M tensor identity of X. M tensor identity of X. So this is a way to write a tensor of two morphisms. You just put them in a row this way. So you don't put any symbol, you just put them together this way, and this means tensor. And then you compose with multiplication, which means when the composition, so the tensor is writing horizontally for tensor, and for composition is vertically. So here, composed with M, here mean you compose, so you write vertically. And equal, so identity of X multiplication, and then compose with, okay. So this is the picture for the associativity axiom. And then for the unitality axiom, unitality axiom, same exercise. So E, you put E, tensor identity of X. And then you compose with M. That's the identity of X. So the vertical line, it's the picture for the identity. It's equal to identity E composed with M. Okay. So it's, yeah. So what this is saying that when you have the multiplication morphism. If you put a dot here, you can delete everything there. You just have one string, one vertical line. Or if you put a dot here, remove as a vertical line. So you put a dot here, it means that now you have one. So you just have a morphism from x to x. Here is one, and one is, as you said, you can omit. And this is identity. So by definition. Okay. Okay. So same definition. I will go quickly for co-unital coalgebra. Definition. So for co-unital coalgebra. Maybe I can cheat if I will try to cheat, maybe. Yeah, let me cheat. I will copy and paste. Where is that? Because in fact, this is similar. Copy and paste. Okay. So, no. More there. Okay. So, co-unital coalgebra. Co-unital algebra. So, what should we change? Co-unital coalgebra. So, we should change. So, it's a triple. Here we change, we write delta epsilon, where x is an object in C. Delta is a co-multiplication morphism in x from x to x tensor x. And epsilon is a co-unit morphism here from x to 1. So when you put a co-unit, co-algebra, in fact, you just reverse the sense of the arrow. So it was from 1 to x, so now it's from x to 1. It was from x tensor x to x, so now it's from x to x tensor x. Depicted as follow. And here, yeah, I don't know. Yeah, let me write it directly. I don't know how to rotate the picture. Let me try. If I don't, I will draw it. Copy and paste. Can I rotate or not? No, I don't know how to rotate. So I will draw it. Okay, so co-associativity. So this relation, at least I can copy this one, are depicted as follow. Okay. Sorry. No. Okay. So co-associativity. Co-associativity. But basically, the rotation, so a rotate of 180 degree rotation of this picture. I forgot. I forgot to write the action first. So before sorry, little bit. Before writing the picture, I have to write the axiom with formula. So this satisfies the following axiom. Sorry, but anyway, this is similar. This satisfies the following shows co-associativity identity X tensor delta composed with delta equal delta tensor identity X compose delta. And co-unitarity is epsilon tensor identity of X compose delta equal identity of X equal identity of X tensor epsilon compose delta. And you see, this is very similar to what we have here. Just reverse this, where you just reverse this and this, and maybe this and this. The same here. And replace m by delta, e by epsilon, etc. So this is just the formula representing pictorially. You are just making 180 degree rotation. So pictorially, this is just doing this way. So delta. Oh, I forgot something else. Yeah, I also forgot to write depicted as follow. Yeah, sorry. So delta depicted as follow. So delta is this way, and epsilon is this way. Okay. So just a rotation. So by trying to make quicker, maybe I lost time. Anyway, so you just make the same picture. This transformation. So the co-associativity is just, so you have delta. First you put delta, and then identity tensor delta equal delta and delta tensor identity. Okay. And for the co-unitarity, it's so delta then epsilon identity equal identity of X equal delta identity epsilon. Okay. So that was for algebra and coalgebra, unital and counital. Now we are interested in Frobenius algebra. So we need to define, to provide an extra constraint connected the two structure of algebra and coalgebra to define the notion of Frobenius algebra object in a monoidal category. This is very general, very general. Okay. So, object algebra in the monoidal categories. C is given by the data of five things. So what we call the quintuple for five, quintuple, x, m, e, delta, epsilon, where x, m, e is a unital algebra, is a unital algebra, and x, delta, epsilon is a co-unital algebra, coalgebra. And satisfying an extra assumption. So they must satisfy the following axiom. So called the Frobenius axiom, involving all these ingredients. The algebra and coalgebra ingredient. In fact, in the Frobenius axiom, there is no, it do not involve unital and counital, just algebra and coalgebra. But the mixed algebra and coalgebra morphism. So identity of X, and of course there will be a picture very clarifying for that. Identity of X tensor M composed delta tensor identity of X equal delta compose M equal M tensor identity of X composed with identity of X tensor delta. Okay. And the picture is as follows. This relation typically illustrated as follows. So the Frobenius relation in picture is as follows. So you start from delta identity. Then you compose with identity M. That should be equal to, so M composed with delta, that should be equal to, here you have identity delta composed with M identity. Okay, so this is the picture, the very famous picture for Frobenius constraint. So for some technical reason, we will introduce what we will call weak Frobenius algebra, but in fact, we will we'll see that it's only for technical reason because we will be able to prove that weak is equivalent to full. But in fact, what we call weak is that we only keep this and this equal this, and we omit that. So this is not in the literature. So this is our own notation for this paper, for this class. I don't think this is written in the literature because in fact we will prove that weak is equivalent to weak Frobenius is equivalent to Frobenius. But for some technical reason, it will simplify some proof to use this way. But anyway, It does not matter too much. It's just a technical, but we will write it. Frobenius algebra. Okay. So we define a weak Frobenius algebra by relaxing the Frobenius condition in the following way. So weak Frobenius and so as I said, only the left and the right hand side of the equality. So this, so this equal this. And not the one in the middle. Okay, but as I said, we will demonstrate. We will demonstrate in the coming lemma 2.7 that an algebra is weak Frobenius if and only if it is Frobenius. That an algebra is weak Frobenius if and only if it is Frobenius. Okay. So here is the first. So 2.7 will not be the first lemma we will prove. The first lemma we will prove is the following lemma 2.4. And I will write the statement, but prove it after the pause because it's almost time for the pause. So let x m delta e epsilon be a weak Frobenius algebra. So in fact, what is the point of weak Frobenius algebra? That there are many intermediate statements, and many lemma which can be proved only using this relation. Some basic result, we don't need this equality. We just need this equality. For example, this one. So be a weak Frobenius algebra. Then X is self-dual, which means X star equal X. So I already recall last week what is the meaning of dual. And so you have evaluation, co-evaluation map, etc. Meaning it's another object, Y, and some evaluation, co-evaluation map satisfying some zigzag relation. And in fact, you see these zigzag relations are closely related to look like this Frobenius structure. In fact, it's not a coincidence. In fact, we will see. So, what kind of it is self-dual for which evaluation and co-evaluation map? So remember, a dual of an object is the data of another object and two morphisms called evaluation and co-evaluation are satisfying zigzag relation. So if we want to prove that it is self-dual, we want to prove that it is its own dual, so we need to provide an evaluation co-evaluation map from x tensor x to 1 and from 1 to x tensor x. So with satisfying the hexagonal, and we will prove the hexagonal using the weak Frobenius structure. So with the evaluation morphism define. So I will finish the statement and make the pause. Define as fx define as epsilon compose M. So I will draw a picture, and the co-evaluation morphism defined as co-ev x to be delta compose E as illustrated below. So the evaluation map usually in graphical calculus you write the evaluation map this way. So here is defined as M composed with epsilon. So epsilon composed with M. So when you read from top to bottom, so you start from. That's why some people prefer from bottom to top, because in fact, it's like drawing from top to bottom. It's like reading from right to left, because you start by M and then you put epsilon. But yeah, so first M. So the input start from here. So M and then epsilon and then output. So it's this way, and then the co-evaluation map is usually depicted like that, cap and cap. Usually this is cap and cap, and this, so it is E, so composed with delta. Okay. And so after the pause, we will have to show that this equal identity equal this. So when you compose evaluation map with co-evaluation map equal identity equal this composition this way. So when I say we compose, in fact, it's not that we compose this way. It's that you put identity here, so you identity co-evaluation, and then evaluation identity. But anyway, so we will, after the pause, we will prove that directly by graphical calculus. We will just need weak Frobenius and unitarity co-unitarity. So the proof after the pause. So proof. So we will make the pause. So from 6:10 to so sorry for I shifted the pause by 5 minutes. Does not matter. Okay, pause. Okay, so the proof. So we want to prove the zigzag relation. Okay, the zigzag relation is as follows. So this. So you start from that. This. So only pictorial proof. So the following diagram illustrate that this and this no. satisfies the zigzag relation. Satisfy the zigzag relation, which is the axiom when you define a dual. So you can see in Egno book, so I cited before, definition 2.10.1. So in this book, they don't say zigzag relation, they just provide the relation. But for short, I say zigzag relation, but be careful. It's not written zigzag relation in the book. Okay, so pictorially, it's as follows. So you start from, so what do you want? You start from that. So you have this, which is equal to. So here you have, so remember that this is like that. So you have to put it like that and to put like that. Okay. So this is, so let me try to make the picture a bit more beautiful. So this is equal to this way. So now we are in our the setting of our Frobenius algebra. Now you apply the weak Frobenius. So now let me make some color. Yeah. So now you apply the weak Frobenius assumption, but only here. Okay. Because remember that here you can see that you can do that because you have this, and here you compose with identity, and here you compose with unit. Here you have this morphism, compose identity unit, and here you get co-unit identity. So it makes sense. You can isolate this part, and then you can complete, and so you can apply the Frobenius, the weak Frobenius assumption here. So here you apply the weak so you apply weak Frobenius. What do you get? So weak Frobenius is this equal this. So you can replace. So here we have this picture. So you have this picture, and you can replace this picture by this picture inside. So you replace inside. So what do you have? You have something like that inside, and you put the extra data, the missing data. So you replace that by that. Now you have to put this. So here you put this, and this. Okay. So this is a weak Frobenius assumption. Now we will apply the unitality and co-unitality. So here you see you can isolate here you have no change. Here you have unitality and co-unitality. So here and here. You have unitality and co-unitality, which is that. something like that for co-unitality, something like that for unitality. So the fact you can draw this the size of the string here make no specific sense. So even if this do not stop at the same level, it does not matter. For example, here, you take this piece and you see this one stop before this one, but it does not matter. You can apply this is topological if you want, in some sense. So yeah, so you apply unitality and co-unitality. So this is equal to identity. So why? You have co-unitality and unitality. So this is just identity. So this you can replace by identity. And this also just identity. So at the end, you just have identity, compose identity. So just the identity. Okay. So from that, this is unitality and co-unitality. Unitality and co-unitality. So I write this way with parentheses. Identity. And the rest is similar. So if you start so you start from here. If you start, so maybe I will need more space, but it does not matter. If you start from that, which is this way, and you apply what? With Frobenius, again, you get something like that. And you apply unitality, co-unitality again, you get identity. Okay? So what you can say is anyway, you can reapply if you want. You can start from here and get identity. So you will get this equal this as we want to prove, or you can just do linearly. So this equal this by definition, equal this by weak Frobenius, equal this by co-unitality, and equal this by co-unitality again because you apply. This is identity compose identity. So you replace this identity by this picture and this identity by this or the other. This one by this one by this one. So by co-unitality you get that. And then by weak Frobenius you get that because you replace that by that. And then by definition you get that. Okay. So you prove this way the zigzag relation, which is this equal this equal this. Okay, and that's all. In fact, this is the end of the proof. So we write this little square for saying that this is the end of the proof. Okay. Okay. So you see, so I have to go slowly to explain each step, but in fact, when you are really used to this kind of setting, the proof is, you can almost say the proof is straightforward. The proof, you draw the picture, it's immediate. In fact, this kind of picture, was defined, or was to make this proof straightforward. Remark 2.5. So a little technical remark. So when you consider a monoidal category, so when you say just monoidal category, there is no dual structure a priori. But when you say a rigid monoidal category, rigid means every object has left and right dual. And you can say, you can fix a rigid monoidal category. So you fix a right and left dual for every object. It is fixed at the beginning. This does not imply that what you will get this way will be the one was fixed before, because you can have other choices. But in fact, it was proved in Egno book that if you have two different choices of dual, they are more or less isomorphic up to a unique isomorphism or something like that. So I don't want to go into this kind of details, but you may have several choices for a dual, but two different choices may not be equal, but they are isomorphic in some sense. So the definition. So be careful. Definition fx this way and fx this way may not align perfectly with a given rigid structure in the monoidal category. What is important in the sentence is the given with a given. If you first give a rigid structure and then it may not align, but of course you can first define that and make a rigid structure where this. So if it depends if the rigid structure is given before or after. Rigid structure in the monoidal category. However, it is possible to adjust the rigid structure to achieve a perfect match, as noted in Egno book definition 210. Additionally, rigid structure on an object is unique up to unique isomorphism on an object so definition 21011, I guess this is definition of rigid monoidal category. 21011. Yeah, 21011 is an object in a monoidal category is called rigid if it has a left and right dual. A monoidal category is called rigid if every object of C is rigid. Okay, so additionally, the rigid structure of an object is unique up to a unique isomorphism, as I said, as stated in Egno book proposition 210.5. So in this paper, we will assume that this alignment is always satisfied. And that will simplify a lot proof. We will assume that this alignment is always satisfied. So this is like Maclaurin's strictness theorem. It's always possible. So you can assume without loss of generality. But sometimes you have to be careful. So, for example, with Maclaurin's strictness theorem, when you deal with F symbol, okay, the F symbol are not trivial. But the F symbol represents so there are always something hidden. So you have to be careful. Okay, so we will assume that. We can assume that without loss of generality, so it's good to assume. So lemma 2.6. So I discuss with Jürgen Fuchs, and I ask him, is there an issue of doing this assumption in general? And he said, I forgot. He said about left and right dual. When you, if you are in a category, if the left dual is distinct from the right dual, which is not the case here because it is self-dual. So its left dual equal to it, right dual equal to itself. So there is no problem. But if you choose a left dual distinct from the right dual object, then you may have it may be an issue, it may be a problem to make this assumption, to this alignment. Okay. If you need to distinct right and left dual to be distinct, etc., you may have some problem with alignment, and then you have to deal with Nakayama isomorphism or something like that. But we will not need that here. So I just mentioned that orally, just to be complete, but we will not need that in this work. So lemma 2.6, a unital algebra and co-unital coalgebra is weak Frobenius if only if the following equality hold. Okay, so we will this lemma will provide an equivalent reformulation for weak Frobenius. So a unital algebra and co-unital coalgebra. So x m delta I epsilon is weak Frobenius if and only if the following equality hold. The following equalities hold. So we have two sets of equalities. So I will write by formula and then by picture. M tensor identity of X composed with identity of X tensor co-evaluation of X equal delta equal M tensor identity of X composed co-ev of X tensor identity of X and evaluation of tensor identity of X tensor identity of X tensor delta equal M equal. So you see how it is boring to write the formula, and you will see how it is easy to see the picture. Identity of X compose delta. So as illustrated below, and you will see this picture.
delta compose, delta tensor identity. The last.
Ah. So there is a typo in the. Let's see. You might be right. So this is one of the advantage of making this kind of class. You can find some typo. Okay, let's see. So the picture will not lie. So you start from so identity co-evaluation and then multiplication identity. This way. That's okay. And this is delta, which is okay. And then you have identity coev composed with wait, yeah, this is no no, this is coev identity composed with identity wait yeah,
Identity tensor multiple. So here there is also opposite. Should be.
yeah, there's a typo here. So identity this way. Okay. Yeah. So let me make. That's strange because we checked that 10 times. And there is always a typo. So on page so lemma 2.6. So here you should write so identity, so coev identity, and then yeah, so identity of x tensor m. Okay. Identity of x tensor m, and the other one should be and so let me see. So delta identity, and then identity evaluation. That's okay. Equal m equal. So there may be an issue here. So let's see if I write. So this, and yeah, that's not okay. So you have to permute here. Should be delta tensor identity of x. Which one? Which one we want to permute? In fact, yeah, this one. Delta tensor identity of x. So delta identity of x and then evaluation identity. Okay. Typo. So it is this. Okay. So this has absolutely no incidence in the paper because everything is done pictorially. Okay. I hope there is no somewhere we have to check it. Sometime we write a pictorial check, but I don't think so because in fact this composition it was written before was make no sense. So check elsewhere. Anyway, so what is the point here? What this relation is saying. So first, this relation are different from the weak Frobenius relation, which is just that. Here we are just saying that. So you start from that and you do that. So this is the same. So now you have the morphism from that x to x tensor x. This is nothing but the usual morphism from x to x tensor x, which is delta. So applying this, it's like that. And do the same here. And same, now you start from that. You apply that, the same as doing that. So, yeah, so that's useful. Okay, so proof. We will demonstrate the first equality using the following diagram, where self-dual refer to the lemma 2.4. So we will demonstrate the first equality using the following diagram. Where the self-dual refer to lemma 2.4. Okay. So you start from here. You want to show this and this. Okay. Okay. In fact, we just need to prove that, because in fact, the proof for that will be similar. So you will prove that by picture, and then similarly, we will prove that. And then, so let's see what will happen. So we start from that. Yeah, so it's boring to change the color every time. So you start from. Okay. Now you apply lemma 2.4. By lemma 2.4, I just say that here, what I did not, by picture, by the formula, you said it involves evaluation, coevaluation. This is a coevaluation, this is an evaluation morphism, etc. So by lemma or by the remark, in fact, we assume the alignment. So we take this. So you replace this by just putting that, which is the same. So you put here self-dual. So self-dual. So by that we mean lemma 2.4. So this is of this form. So okay, and then you apply the weak Frobenius assumption here. Weak Frobenius. And you get something like that. And then you complete. So this, this. Okay, and I no. Yeah, it's okay. I missed something. This, wait. Yeah, this one. Because here you have to put this, and this. So we put this, and this. Okay. And now you apply the counitality. Here. Counitality. Is it counitality or unitality? What?
It is unitality.
Yeah. So another typo. That's really crazy. So proof of lemma 2.6. Proof unitality.
No, it should be unitality.
Yeah, it should be unitality. Unitality. So, by unitality. Unitality, which is equal to. So you replace this by identity only. So you have this. Okay. So that proves this equality. Similarly, this equality, you have self-dual, etc., with Frobenius, and then also some unitality, I guess, and you get that. So the other equality is similar. And similarly for that, because maybe we write here you do that. So you apply weak Frobenius and then co-unitality to that, and similarly here, back co-unitality together. Okay, so there's other equalities follow similarly. So it was, remember, it's an if and only if. So we assume weak Frobenius, so unital, conital, algebra, coalgebra, weak Frobenius, and we get this set of equality. Now we assume unital coalgebra, conital coalgebra, and this set of equality, and we have to prove weak Frobenius. Okay. So conversely, if this equalities hold, let us show the weak Frobenius condition. Frobenius condition. First, okay. First, note that lemma 2.4 can be established as well. So if you replace weak Frobenius by this set of equalities, you can also prove the lemma 2.4 can be established as well. So I will not prove that, but just show you my hand here. If you see here you have weak Frobenius, so you have to put the you have to put here and here and then applying weak Frobenius, and you get that, etc., etc. But instead of putting the two, you put only one. Then you can apply the one of the equality here, and then so you get what do you get? What do you do? So you apply here like that. So you get something like that, etc. So you apply here, you can apply the equality, and again. So it's the same idea. So you can prove the lemma 2.4 similarly for this from this set of equalities, and so we have the self-dual. But I don't even know we need that. I'm not sure. It is required. Let's see. Yeah, we apply the zigzag relation. Okay. So we really need lemma 2.4, so we can prove it, as I said. The next, we have, so you start from that. So we want to show the weak Frobenius. So you start from that, and we want the other picture. So you apply the zigzag relation here. So, zigzag relation. So we will apply it where? Just here. Here you can put some identity here between the two evaluation coevaluation. You can put an identity, and so what do you get? You replace. So you have this something like that. You have something like that. Identity. Something like that. So you want to replace this identity by a zigzag. Which one? You want to replace it by that. Okay. So what do you want? Is to put the zigzag here, and then you put again what was before. Which is okay. So this is so if I draw it more beautifully, you have something like that. 1, 2, this way and this way. Okay. And now you apply just the equality here. So by assumption, you apply the equality from here and so you have by assumption assumption. What do you get here? Is that so this part is replaced by something like that. This part is replaced by something like that. And so we get the weak Frobenius. Okay. Okay. So, end of the proof. And what time is it? It's time, yeah. So we will stop here. And tomorrow we will start with lemma 2.7 saying that a unital algebra and co-unital coalgebra is weak Frobenius if only if it is Frobenius. So the result we mentioned here. Well, here. So tomorrow we will start by proving that weak Frobenius is equivalent to Frobenius for unital algebra, co-unital coalgebra. Okay. So see you tomorrow.